Welcome to qnawire.
Hi, and welcome to a new problem. This time around, we have a proton, and it's it's has a mass of 1.67, times 10 to the 27 kilograms times 10 to the negative 27 kilograms. And this is what happens with the proton. So assume you uh, shoot the proton with the velocity v um, initial of. Well, actually, I'm going to use vi. I have a preference for that. You can use anything as initial, but this is v initial, and it's going at 3.00 times 10 to the 5 meters per second, and there's a uranium nucleus. So right here, this is 5 meters. This is a distance of 5 meters away, and there's a uranium nucleus. So we're just going to show this. This is a nucleus, uranium. Um, and what's happening is as the proton comes this way, it's being repelled by the uranium. So there's a force that's repelling that. There's a force that's repelling that motion by the uranium nucleus, and this force happens to be alpha over x squared, where x stands for the distance between. So think about the proton coming this way, and then it doesn't get to the uranium. Assume this is the uranium, and so there's a distance x between them. This is x, and that's what this x stands for. The alpha itself is a constant with its own value. So alpha happens to be 2.12 times 10 to the negative 26 Newton meter squared. And the uranium nucleus is at rest, so it's not moving. Part A of the problem wants us to find the speed of the proton when x is 8.00 times 10 to the negative 10 meters. So this is how it's laid out. This is the proton. It's coming this way. The uranium is at a distance of 5 meters. So at this point, x, I'm going to call it maybe x1 is 5 meters. And then this gap here, x, is 8.00 times 10 to the negative 10 meters. So so what's the speed? We want to know the speed of the proton when the nucleus is at that distance from when the proton is at that distance from the nucleus of the uranium. Remember, there's a force that's pushing this way from the uranium, and the force is given by that function right there. So I'm going to continue in the next page, where just having a simple diagram. You have the uranium. This point here, I'm calling it x equals to 8.00 times 10 to the negative 10 meters. And then the uranium is at x, I'll say x1 equals to 5 meters. Remember, work, if the force is constant, it's force times displacement. But the same work, if the force is a variable, it becomes F times dx. That's a variable. The question is, why do we need to know the work involved by the force? So the force is the force from the nucleus of the uranium, F. It's a variable force, and it's working against the motion of the proton. It's a variable force. It's working against the motion of the proton, and therefore there is energy expended. Okay, so there is some energy involved. So we can use the work energy theorem, which says that work is the same as change in kinetic energy. So if you do the integral, the limits of integration will be from so this is we want to find, what's the um, what's the speed when the gap between the uranium and the proton is 8.00 times 10 to the negative 10. That's what we want to find out. If this point right here is the starting point, so it means in your limits of integration, your base is going to be 5 meters. And then our stopping point will be 8 times 8.00 times 10 to the negative 10. Don't forget the force itself, which happens to be alpha over x squared, and then dx, that happens to be the final velocity minus the initial final 1/2 mv squared, 1/2 mv final squared minus 1/2 mv initial squared. That represents the change in kinetic energy. So we are interested in finding the final velocity, before it stops. We know what the initial velocity is. If you can recall from this point, the initial velocity is 3.00 times 10 to the 5. And so if we go back here, we can do our integration, and it becomes alpha times x to the negative 2. Our limits are 5.00, 8.00 times 10 to the negative 10, and then times dx, like that. And this is equals to 1/2 m. We can pull the 1/2 m outside, and we're left with v final squared minus v initial squared. Our target is to get v final squared. And so at this point, we could do the integral. If you do the integral, you end up getting negative alpha over x. Why is it alpha over x? Because think about this. If this is negative 2, if you want to do the integral, you do negative 2 plus 1, and that gives us x to the negative 1 over negative 1. This is just like a side note to show you how you end up with this as an integral. And then you put the limits of integration, 0.5, and up until 8 times 10 to the negative 10. That result will be divided by 1/2 m. And then we end up with v final squared minus v initial squared. Our goal is to get v final squared. So v final squared becomes equal to negative alpha over x, the integral from 5 to 8 times 10 to the negative 10. I could still put the units just because it's physics. Units make such a big deal, so don't forget that. And then over 0.5 m, this v initial squared comes to this side, so we have a plus v initial squared. Just going to move to the next page, go back and see what those values are. So we get v final squared equals to, if I look at the other page, alpha. So we have alpha. Remember, alpha is, if I go back, what's the value of alpha? That's the value of alpha, 2.12 times 10 to the negative 26 Newton meters squared. So 2.12 times 10 to the negative 26 Newton per meter squared. That's the value of alpha. And then we also have x. Now, x is where you're going to plug in the numbers. We have the value of x. And so the top limit is 8 times 10 to the negative 10 meters minus another alpha times 10 to the negative 26 Newton meter squared. The bottom limit is 5. Okay, so we're done with this part. This is the upper part right here. We're done with that part, this one right here. And all of that is divided by 0.5, and the mass, which is 1.67 times 10 to the negative 27. Okay, 1.67 times 10 to the negative 27. And that's given in kilograms. So don't forget the units again, kilograms. And then plus, if you can see, we had plus the initial velocity squared, plus the initial velocity squared. But at this point, we can plug in the numbers, so we have to go back and check what the initial velocity is. That's at the beginning, where we had the initial velocity being equivalent to 3 times 10 to the 5 meters per second. So 3 times 10 to the 5 meters per second. This whole thing is V final squared, but we wanted to get the V squared, so we wanted to get the V final by itself. So that means we can ignore that, the square itself. We can ignore the square itself, as long as you remember to put the square root sign over all of that. Okay, so it's a whole process in trying to solve the problem. One of the things you want to that's going to come out is that this numerator is going to be a negative number. When you do the math, you'll find that the numerator right here will be a negative number. And that's understandable because this second part of the problem is divided by a bigger number. Okay, so you get a bigger number on the right than on the left. So, negative 2.12, we had a negative number, so don't forget that. This one right here is a negative number. So we have to come back and put a negative right there. So there's a negative right here. Okay, and then you're subtracting it from another negative number. So a negative and a negative is going to be what? It's going to be positive, right? You're subtracting from a negative number. You're plugging in those values, 8 times 10 to the negative 10, and also 5. So we have negative alpha minus another negative alpha. So this is going to eventually be a plus if you do the algebra. And then we also have 0.5 times the mass. This value is squared. Okay, that value is squared because if you go back to this page, you can see that we have a V initial squared right there. So we have all our values right. If you do the math, you get 2.41 times 10 to the 5 meters per second. So that's the velocity, that's the speed of the proton when it is 8 times 10 to the negative 10 meters from the nucleus. In part B, they're asking as the proton approaches the nucleus, like that, there's a repulsive force. So let's assume this is the uranium, and this is the proton, and this is the force involved. It's repelling it, and it slows down the proton until the final velocity is 0 meters per second. So it's going to stop a little bit and it comes to rest. After which, once it slows down and close to a stop, it doesn't get all the way up until the location of the proton. So if you think about this, it's um, coming in this way, and it's being stopped at some point, not exactly where the nucleus is. So there's still a gap of X. Okay. So we want to find how close is that to the uh, to the nucleus of the proton itself. The force is doing some work. It's still doing some work. Remember, work equals to force times distance if it's a constant force, and then work equals to integral of force times dx if it's a variable force. But this is also the same as change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. But in this example, remember the final velocity right here is going to be 0. And so this whole part is 0. We could do the integral there. As you can recall from the previous section, we have alpha over x squared dx being equivalent to negative 1/2 mv initial squared. We do have the initial velocity. If you do the integral at this point, you get negative alpha over x equals to negative 1/2 mv initial squared. We want to solve for x, and so when you flip things up, the minuses cancel out. You flip x, you get x over alpha equals to 2 over mv initial squared. And so that means that your x equals to 2 alpha mv initial squared. Like we've always mentioned, uh, you want to keep, I'm just going to complete the problem in the next section. So x is 2 alpha over mv initial squared. X equals to 2 alpha over mv initial squared. It's always a good habit to keep your variables up until the end. Remember, alpha is 2.12 times 10 to the negative 26 Newton meter squared. All of the mass happens to be 1.6. 1.6 times, actually is 1.67. If I go back, you see the mass is 1.67 times 10 to the negative 27. And so that's what we have right there, 10 to the negative 27 kilograms. Also, we have to plug in the velocity, the initial velocity you can see from the beginning. Slide 1 is 3.00 times 10 to the 5 meters per second. So 3.00 times 10 to the 5 meters per second. That's going to help you solve for m, and it comes rounds out to about 2.8 times 10 to the 2.82 times 10 to the negative 10 meters. Okay, so that's the distance it stops. So think about the proton coming this way, and then there is a force coming from the uranium that's pushing it that way. So the proton doesn't get all the way up until the nucleus. This is the nucleus. It doesn't get there. There's a distance x. So we want to find out what that distance is. We know the force produces some type of energy. And that's why in the previous slide, you can see there's a relationship between the work done by the force and the change in kinetic energy. The final velocity is 0. It gives us a relationship where we still need to find the integral. We find the integral. There's a negative here. We simplify the problem, and so we end up getting the value of this is the value of the distance where it stops. Okay, so interestingly, if you go to the next slide, you see that it's gonna stop at a distance where x happens to be 2.82 times 10 to the negative 10 meters. So it doesn't go all the way up until x. So this is like a certain x, and this is x1. X1 happens to be 5 meters. So there's a gap. There's a gap right there. Okay, so we want to find, what the velocity of the proton is. What's the speed when it goes 5 meters away. So this distance is 5 meters. And this gap x, which is saying how close does it get to. So it gets to a distance of x, which is that. So we want to find what's the velocity, what's the speed when it's again 5 meters away. So final velocity at this point, which is 5 meters away. Remember, the work energy theorem says that it's going to start at 2.82 times 10 to the negative 10 meters and end up at 5 meters. But even though it ends up at 5.00 meters, we still have to do the integral alpha over x squared and equate that to the change in kinetic energy. The change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And you can recall that the initial velocity when it stops. So when it stops right here, the v initial, when it stops, happens to be 0 meters per second. That's the initial velocity when it stops. So this whole thing will be 0. We just need to find the integral. When we do that, we get negative alpha over x. The limits of integration are 2.82, not 2.82, 2.82 times 10 to the negative 10 meters up until 5.00 meters. And that gives us equals to negative 1/2, or rather not negative 1/2, but just 1/2 mv final squared. So I'm going to simplify. Oh no, I need to erase that. So these problems can be long and tedious sometimes because of the algebra, but you just gotta be patient. V final squared. So imagine you're gonna divide both sides by 1/2 m. And that helps us get the value of V final is the square root of negative alpha over x, the integral from 2.82 times 10 to the negative 10 meters up until 5.00 meters. That has to be divided by 0.5 m. Remember, m is the mass of the proton, which happens to be 1.67 times 10 to the negative 27. So we have to be very careful about the units. Okay, so always keep track of all the units. So this one becomes radical. If we plug in the numbers, we get negative alpha. Alpha is 2.12 times 10 to the negative 26 Newton meter squared. That's the top part of 5.00 meters. That's the initial plug-in. And then you subtract another negative. If you subtract another negative, it becomes negative. I'm just going to write that one here. Negative 2.12 times 10 to the negative 26 Newton meter squared. That's the other limit. We have two negatives now, and then you also have this x, which is 2.82 over 2.82 times 10 to the negative 10. That whole result at the top has to be divided by 0.5 times the mass of the object. If you can go back, mass of the proton is 1.67 times 10 to the negative 27 kilograms times 10 to the negative 27 kilograms, like that. Remember, the radical sign goes all the way, so you got to be very careful. If you solve that problem, you get that the final velocity, which I'm gonna put right here in the middle. Well, actually, I don't have to put that in the middle. I can just change this radical sign a little bit to give it some space. It becomes V final equals to approximately 3.00 times 10 to the 5 meters per second. That's your final answer. So this is the final velocity when the proton has been pushed back. Okay, so remember, it stopped somewhere like right here a little bit, and then it was pushed back all the way to the beginning, which is 5 meters away. That's why we have 5 meters right there. It started at 2.82 times 10 to the negative 10. Tedious problem. It's a long problem. So you want to take your time at the beginning. We started off with a proton that's going towards this nucleus, and we wanted to find the velocity of that proton. We had certain constants from the force, so we're given a force that's opposing that motion, and so we used a work energy theorem. Remember, it's a variable force, and so the work itself is equivalent to change in kinetic energy, and so because the work is a variable force, we have to do the integral. And if you do the integral, you end up with a specific value. You have to solve for the initial. You have to solve for the final velocity. So to solve for the final velocity, you notice that the v initial moves to the other side. It moves to the left, right there, and so you have a new way of writing the problem. It's, you can take any kind of approach you want at this point, but it's always a good habit to solve for the variable you're looking for and then wait up until the end. If you see right here, you wait up until the end to get the v final. So you just plug in the numbers and then get the v final. So after you get the v final for that, the next part of the problem was, what's the distance between the uranium nucleus and the proton once it stops. So when it stops, it means that your v final is going to be 0. This v final right here is going to be 0, and so this part of the problem is eliminated. You don't have to deal with it. It's gone. You're only left with this part of the problem, 1/2 mv initial squared, the initial kinetic energy. This is the work done by the variable force. We need an integral there with respect to the x, and so you compare the two values, and again in the same light, you solve for x, and that's what we have. And then in the next slide, you can see once you solve for x, you plug in the numbers, you get that position 2.82 times 10 to the negative 10. So I hope it makes sense how we process this problem. Just take your time to look at each and every single step. The math is actually heavier than the physics itself. The physics is just about a force versus work done by the force repelling the proton against the uranium nucleus, and then you have specific points of displacements which are critical to computing the integral of the force, and that gives you the work. Thank you very much. I hope you enjoyed the video. Feel free to send any questions, and looking forward to the next problem. Have a great day. Okay, bye.